So the PSoC creator looks like that. And at least I got the PSoC creator 4.2. I think that's because I had the link to open the 4.2. There's also already the 4.3 is out, although don't install that one this week, since it's not usually a good idea to install new version. Start on one version and then continue with another. There's always some small glitches happening. But anyways, the creator, that's an integrated development environment. So it means that it has separate different kind of views here. So that's where it starts from basically. Currently, we don't have any workspaces. Workspace equals to project. Or actually one project could have, say, let's see. The one, yeah. Basically, it would be one project has one workspace, unless you have a device on a project that is designed for more than one task, meaning the application environment. So you could have a multi-purpose thing that you have a switch, for example, switch as a mode switch that changes the behavior of the system. For that kind of things, you could have more than one workspace on one for the one project, but usually it's project equals to workspace. Okay. Start page. That's a pretty good place to start actually. Learn. One way to learn how to use PSoC is go by this one here. Get acquainted new info about your news and information. Start. Okay, that's the most important probably, I think. Create a new project, open existing projects, or find code examples. And then when you have these Cypress kits, you will also have the this one here. Let me open that one. All the kits you have, learning kits you have, will appear here. And I have this HE kit 059. And it also comes with three the examples. These are example designs. Okay. When you take this processor out of the box, there's actually one place where you can peel it with, so you can actually also tape it back. Not like that. Okay, so do I get it out here? Yeah. When you plug this one in, it has this project already on it. PSoC5LB blinking LED. So if you put this one on the USB port, by the way, you can also get a cable to maybe could you share the cables? It's easier to play with, at least in my case. So some extension cables have some flexibility. There we go. When you plug this into a USB port, well, it starts blinking the LED. And the project actually is exactly that. PSoC 5 LP blinking LED. Okay. Then there are a couple of other things. There's the power LED, that's the orange light. That is lit when there is power from USB. And then there's also that green is a status, which blinks when you transfer the code there. Okay. But let's start something else. Our first design will be designed from scratch. I kind of don't like this method of taking an example and thinking how it works. Yeah, sure, you could do it that way, but I'm different generation professor. I'm old. I do everything on old school. So we start from scratch, which is actually not that scratch as you could think, since there's plenty of already done things here. So let's create new project. Click on that one here. And select project type. Okay, target device. Design project for target device PSoC 5 LP. Okay. That's the selection tree, and anything else than PSoC 5 LP would give you some trouble, like not working anything. So PSoC 5 LP. And well, then it also gives you this processor device here, last used CY8C5888. I think you have this one as selection tree, or let's see. Yeah, that's CY8C5888LTI LPO97. That's the processor what you have on this design. And by the way, that's the high-end processor of this 5LP series. Not the low-end, but high-end. That has all the gadgets. For development purpose, you want to have the biggest processor available with biggest memory. And then when you have a design, then you can go and choose the lower grade. The porting from one processor to another would be quite straightforward task. Okay, and then click next. Next. And we start from empty schematic. You can start also from code examples. That's okay when you are doing a, say, some real project. Then you can start from somebody else's project or your previous project, of course. Or in this course, you will be starting tomorrow, you will be starting the project based on what you did today. That's fine. But today we start from empty. Okay, empty schematic. There, next. Workspace name. Rename that one to something. For example, what your project would be today, for example, PSoC Design 01, like PSoC Design Course First Workspace. Project name here could be the same as workspace name. It can be also something else. I would use the same. So this here workspace name actually affects on the location. I think here we have the, but anyways, let me go and simplify this a little bit, since this is a strange looking location. I don't want to have that on. Let's see. Strange. Projects. PSoC design 01. That looks better location. Okay. I don't care what you are putting here, as long as you find your project on your computer. It's your design, it's your computer. You can mess it up as you wish. But anyways, the naming convention should be something that you understand. You remember after 2 months from now. So think of a situation that you are actually working for some company already, part-time or so, and you need to find what you did today. Okay. Name the project files on a with the name that means something, and also put it on the place that you find it. All right, finish. And the view changes. That's something new on integrated development environment. It starts with the hardware sketch or circuit sketch. So we are not starting coding, but we start by designing the system. And on this design we have building blocks. The building blocks are here on the right. There are some analog, totally analog. Just a moment, I need to do some. Okay, there we go. Analog. Analog functions. Let me open a little bit of that. You can choose these building blocks. Different types of A to D converters, amplifiers, analog multiplexers, comparators, D to A converter. You can, if you find it impossible to route by this automation, then you can route the signals, analog signals yourself. Good luck with that though. And so on. So it has different analog function, well, the building blocks. Oh yeah, sample and track and hold. That kind of thing also. That you would use with the success approximation ratios type of analog to digital converters. Then it has, just a moment, let's go through these. Capacitive sensors. You can put one capacitive sensor block here, but it can have a different kind of capacitive sensors connected to this device. So this is just a function to read the capacitance. Okay. Communication blocks. Oh, wow. CAN controller. I would guess the automotive technology could use some of that, since Nowadays, I think almost all car manufacturers are using CAN buses on the, or some variants of those in their cars. I have motorbike which has CAN bus. File systems, interesting. Since basically you can put some okay, EM file SPI mode, meaning that you can put a single of these SSD cards or SSD card reader there, and you have a block. You just read and write to the card. That's nice. I2C. I the master or slave on I2C. I2S. Lin. There are so many things that I haven't even used. I haven't got any use for it. There is also this old school word here. There's SPI bus, USB bus. Okay, that's what I warned about. The USB would take a little bit longer time to actually start working, unless you start from a ready-made design and then just add something to it. So if you want to have a USB mouse, for example, there is an example of the USB mouse for this target, and then you could just put your own sensors there. And it would look like any USB mouse. But anyways, lots of different communication methods. Then we have digital functions. Wow. There are, pseudo-random generators and PWM, whatever what we have there. Then we have logics and or so on. So even just simple logic files. So if you have two hardware blocks, then you can take the outputs and put or and or something like. Combine these combinatory logic in addition to these block functions, which is nice, since then you basically, when more you have things on the blocks, less code it requires. So those digital and analog blocks are running. You just have to start them and configure and stop. It runs independently. Okay. Logic. Then, okay, there's also access to the control registers and status registers. They're also there as blocks, building blocks. Let's see, what is utility? Nice. Second one is really nice. Debouncer. If you have a switch, mechanical switch, electromechanical switch, you usually get some debouncing of the when it on just close enough, or the connection is done. It usually bounces a little bit like that in micro level, and then it basically, instead of just one pulse, you will get a lot of pulses, and then it stabilizes. That's probably one of those classical exercises in programming of microprocessors that you go through. It's usually on the first microprocessor computing class. How to make software debouncing. Okay, that's how you do it. You add a debouncer to a line which may have some bouncing. Okay. Then there are some others, down counter, edge detectors, and so on, pulse converters, sync, so on and so on. So plenty of different utility devices. And so on, yeah. Display, filters, port spins, power supervision, system, thermal management. all as a building block. Okay, let me take a quick look at the exercise. It's probably here, yeah, exercise 1, and what should we do? Okay, we started from the scratch, adding modules, we'll go through those. Okay, let's go and let's do this one together to get the idea. Then I'll let you to figure out the following part, which is pin input. Okay. So, how to add digital output for this? We take a let's see, ports and pins. We know that let's see, what do we know? Add a digital output pin to your design and rename it to LED 1 and connect it to pin 2.1. So basically this blue LED here is in on port 2, pin 1. Okay, and then yeah, write a piece of code on how to add the first digital output. We will drag and drop the digital output pin to my design. There it is. Should I go and expand it a little bit? Control plus and minus work actually here, just like in Windows overall. Okay, now we have a pin. Double clicking, it gives you the menu to change it. So first I want to call it LED 1. About the block, this block naming convention. All of these blocks have a pre-written APIs, application programming interface. And that name is on the beginning of that API, this generic functions. So use something that makes sense so you can recognize that on code. So that's basically why you should never use just that generic name, pin 1, pin 2, something like that. Then you need to have a translation table. Okay, pin 1 was LED, pin 2 was the button, and so on. You want to name those corresponding to the function. Okay, there we go. Pins. Type. Okay, analog. No, it's not digital input either. It's actually an output. Yeah, digital output. Okay, here is quite misleading, easy to misunderstand. What means hardware connection? Hardware connection on this context means inside of the chip. Port pin has hardware connection, of course, but not inside of the chip in that sense. This hardware connection would be something that you could then connect an internal block, another block, for example, PWM block output to that hardware connection. But in our case, I want to have a software controllable the output. So I will click that one off. So this is just a digital output without internal hardware connection. Yeah, and then, okay, you can also make it bidirectional, of course. Well, of course, this is a processor. Different kind of ways to control how the pin actually works. Quite often these microcontrollers, you need to write yourself a code to access this the pin, the drive control. Same thing here, but there's also the application programming interface which does it for you automatically. So you do not need to set mysterious bits yourself. That IDE is taking care of that. Anyone who has been writing code with the 8051 variants? 8051 variants usually have this open collector output. So no problems, mostly no problems on the driving, but it always requires some the external components. This actually, let's take a look at the drive mode. You can set up the output open drain, for example, which drives well, high driving open drain or low driving open drain. Then it also may have resistive pull up, resistive pull down, resistive pull up and down. Then high impedance digital or high impedance analog. So each of these pins actually can be selected as input or output of any type, practically any type. Okay, so, but this is output. You want to have a strong drive, meaning it must support enough of power to lead that LED. Initial drive state, low, yeah. Depending, of course, if it's high active or low active. Yeah, minimum supply voltage, don't worry about that. Then interesting hot swap, meaning that does it actually also include some protective diodes for hot swapping. The problem with the hot swapping is basically these peaks that come from the inductive wires. Hot swap may actually kill the device unless you protect it somehow. All right, what else? On the second page, mapping. Okay, you can actually have multiple bits making a bus. For example, on this parallel LCD drive, the LCD, the displays, there's a 4-bit interface. So you could make a 4-bit interface by making it a bus. But okay, yeah, that's the most useful for these kind of things. Continuous with basically forces placement in adjacent physical pins. Yeah, and the display as a bus actually gives you some flexibility of which pin is which on the bus. Okay. What else? Reset. So what happens on reset? Power on reset. What do we do with the pin? If you don't do anything, then it basically goes when you press the reset button, it goes first into undefined state until you have initialized it. If that is a problem, then you probably want to put it either low or high after reset. But otherwise, if it's just blinking LED, I don't care. Yeah. High Z analog pulled up, pulled down. it may have some effect on some designs. Okay, built in. Well, don't worry about these too much today. We might actually come back to these some other days, but I doubt that. Then I click apply. Oh. Okay. Before closing this one, actually, there are quite comprehensive data sheets for each module. You can open it here. You can actually also open it from here. When we are writing code, you have also the blocks right here that you can open the data sheet. As I said, these data sheets are quite comprehensive, meaning that it has much more information what you actually are looking for. So there are, yeah, lots of information. How to use it. Also some chip specific. So this PSoC 4 has a little bit different pin blocks than the PSoC 5. And then the component parameters are explained here. And so on. Let's see, does it have the, yeah, it also has all the characterization and such kind of things, slew rates. Yep, mapping. Does it also have the API here explained? Clock. Oh, yeah. Oh, okay. And then the functions. As I said, they are all the blocks also include also the this application programming interface. So functions you can use. Initially, for example, the reading a pin would be done with this kind of function. But again, remember the naming convention. Now our pin is called LED1. So this function is, corresponding function is LED1 read. Okay, but we are not probably reading that value, but more like writing LED1 write. Okay, you can also change the drive mode by software. This is pretty handy if you have, you know, for example, you need to use that one on some of these, let's see, communication protocols when you need to change the drive from strong to, for example, pull up or high Z, depending on what state are you on the communication. For example, the one wire has the pull up resistors, and then you just drive it low. Okay, for the setting the low, but basically there are on that one you can play with the set drive mode to have a constant 0 as you on your initial data register value, and you're pulling it down by setting the drive mode to the strong for that time when you are driving it to 0, and then when you want to release it, you just put that one to pull up or high Z. Okay. And then a couple of other functions like interrupt. Don't worry, we are not going to interrupt today, maybe. But tomorrow we will be going to do some interrupts. And with this system, I would say that playing with the interrupts is easier than in any other environment what I have seen. It takes a lot of magic out of the interrupt. Yeah, and then clear interrupt. Well, this is ARM processor. After serving the interrupt request, then you need to also clear the interrupt. Okay, and also the function documentation is here with the side effects, explanation of the side effects. Okay, that's fine. Now we have LED. Somewhere, did you notice something is missing here? Pin, port and pin. I haven't set up the port and pin yet. That actually is done here. So design wide resources. This section actually gives you the pin out where you can then set the pins. If you click that, double click maybe, it gives you the pin out. And now we can see we have a module LED 1 which requires the hardware, the pin out. You select port 2, pin 1. Port 2.1 there. Yeah, like that. Yeah, okay. That pin actually is the pin on that 100 pin box, the chip. And it shows nice diagram. It's right there. Or in this one, it's right that one which blinks. Blinking LED. Good. If we had analog functions, actually, then you can actually set some of the parameters. You have access to different clocks also. You can set up the clocks by hand. There are internal clocks and internal dividers that can be used either on the blocks themselves, or you can also modify all of that stuff yourself. Interrupts. Okay, if we were about to do the interrupt services, so that's the place where you can actually put the set that what is that? The priority of the interrupts, for example. If we had some bigger memory requirements, then you can use the DMA controller there. For example, communications. The DMA is one way to make sure that if you have a burst kind of data communication, that you save the data somewhere else and let the DMA to work, and at the same time your processor can process something else. Yeah. System, well, it has some parameters. You can take directive / security. Yeah, okay. This device has the flash inside, which can be also used as EEPROM. But also flash can be also programmed so that you cannot anymore read it for example, by some software tools. How to protect your code. That is how. After you have set the lock on the those pins, then you cannot modify that part anymore, and you cannot read that part anymore, meaning that it makes more difficulty for your friendly neighbors in the big one, friendly neighbor who has a tendency of copying software. That prevents copying of the software. Okay, yeah. It also shows some of these header files and source files here. Okay. Currently, we have only one source file, which is the main.c. Okay, when you start a project, then basically you automatically get an empty main file. We have now this nice design and pin out. And the question is, where is the API? They actually should show up as code, right? Well, there's a magic button called, where is it? Not that one. Was it that one? Yeah, generate application. Small button here. Actually, it has So it's fourth on the left. So the first one here is build. We don't have much to build yet since we don't have code. But there, fourth one on the left, that's the generate application. And wow, I generated the application, and I still have the main.c and then this cy API callbacks.h header file, but then it generates code for you. So this is the application programming interface, which has the subroutines for controlling LED1, plus the routing of that one into port 2.1. Okay. Good. All done in this part. Let's go to check the main. Okay, double click. There we go. It's not totally empty. It has a couple of important parts already. This one here, this is the main header, the main commenting lines. You should actually mark your own name and such kind of things. Your own copyright information on the top part. You might also put there the explanation what this program is going to do, something like that, what it's supposed to do, that kind of thing. So my suggestion is that whenever you start the main file, yeah, you fill that information with your own stuff. That's how you protect your intellectual property. Okay, all the include files actually, what this one generates will be added into local project.h. It basically includes all the includes. So you don't need to include separately. Well, for example, these side device H, side device TRM H, and so on. They are automatically here. So if you add a component, then basically you do not need to start from the beginning and adding things. There's lots of things are going automatically there. Then, okay, just like in any microcontroller environment, you have the main function. Why it's called function is because there is also the boot.asm, which is basically the boot code that does first call these initialization routines, which are system level routines first, and then calls the main.c. Okay, and main.c is a function that should be never ending. So it should end to forever loop. Or actually, it also could be that you do your application code inside of a forever loop. Otherwise, if you exit the main function, it returns to the boot after calling the, how do you know what is after, happens on the boot code after that? You don't know. So don't let the processor ever exit the main function. Okay, anyways, so enable global interrupts. That's nice. We have 32-bit processor. I'm quite sure that there are already quite a few interrupts are still already there that we don't see. That's fine. There's plenty of things like, okay, one interrupt is always there. Reset, that's an interrupt. Halt processor is an interrupt. Wait something, that's also interrupt. So that's a good to have the global interrupts enabled at the beginning. Then there's place for the initialization code, and then place your application code here. What I would like to do here is to first, since we have this LED one, I would like to have also the, let's see, where's my LED one? What happened? Huh? Oh, sorry. Documentation. Wow. System reference code, a reference guide for pins, and let's see, there's source. Okay, this seems that there is also the documentation. So this basically gives you the help file. So basically you do not need to have tens of different displays. You can basically rely on that integrated development environment. And there, let's see, let's go down here. Oops. Where is the application programming interface? Read, write. Trains. Power management. There's also pin sleep and pin wake up. Wow. I was looking for the where's the pin start? There should be actually a function called okay. Seems that this does not have it. Usually all of these functions, the initialization means that you need to start that device. Anyways, let me try something here. On initialization, all of the functional blocks that you have installed there, included in the project, you should start them first. Let me take a look what kind of functions do I have here. Wow, there's lots of different things. Do I have the start? No, it's not there. Okay. So maybe I'll just set the value there. Okay. So if you are not good on writing all the uppercase and lowercase letters, it's better to select the functions from this one. I always do some small mistakes, and then there are also some mistakes that basically can lead to strange behavior, since syntactically it could be correct and it could be actually also the existing thing, and then you think, why this is not working as I want to. it might be that you have just misspelled one small thing and the processor is doing something else. Okay, so it's a good idea to start basically from there. And I need to write a value here. And I start by writing constant 0. Okay, this was one pin only, so basically you put there or the 0 or 1 or true and false. Okay, 0, right. And the LED 1, right 0. That would be turning off the LED. But let's do this a little bit more interesting. I also put there the unsigned character 8 bits long. Was it, or is it uint? Wait a minute. That doesn't. Uint 8. Yep, that's the type. It's really nice when it shows you what type of things are behind of each mnemonic. Okay, uint 8, and I will just put here the LED value and initialize it to 0. So basically I could here then write the LED 1 right LED value to give the initial state. Okay, next I do a blinking LED. My code goes here. LED 1 right. And let me make this, for example, the LED value. Oops. And then just change the LED value to right? Was it like that, the syntax? No, it's that, oh, sorry. That's the syntax, right? Does it make sense? How do you set the, how does it go? Was it semicolon here or colon? It's colon, right? Colon, yes. Not semicolon, but colon, yes, no, it's correct. So, setting up the, if this is 0, then it gives 1. If it's not, then it gives 0. So every other time it turns on and off. That's one way of doing it, without if sentence. Again, old school thing. This is how the teachers usually show them how powerful C language is, since you don't have to use the if statement. Okay, good. Yeah. Let's see what happens. Since now basically what I have here is I have the enabled interrupts, I have the writing 0 as initial state, then I have a loop forever, I write the LED value and then change the LED value to opposite value. And then basically next loop it goes, and so in principle it should go, you know, up and down as fast as this processor can do. Something like 20 meg. Okay, some blinking, but you probably cannot see the blink. So in addition to that, you might also want to slow down that one a bit. There are several ways of slowing down. In this case, this is the first design. It's okay to use a wait function here or delay function. But otherwise, you always should time things by timers and interrupts. Timers and interrupts are the correct way. Okay, see why. Was it wait? No, it wasn't wait. Delay. Ha! Wow. I can find delay function here. Delay cycles, delay frequency, delay. Okay. 32k milliseconds. See why delay? It's supposed to be its own function. Right. It requires one parameter, but let me take a look at, okay. So, see why delay. You will put milliseconds here to delay it a certain time. For example, if you want to delay 1 second, it would be 1000. Okay. Now it should blink the LED with different the frequency. All right, and now I have both the hardware and software set up. I can build my design. So building means it compiles all the code files, then links the those with the libraries, functions, and then makes the hex code. That is the code that the microprocessor actually understands. Good. And then we can go and let's see, program. That's the 0010 and a chip. Next to it, there is a bug. Debug. There should be, you know, red stripe on the top of that, but that would be a debugging mode. But let's go and just. Okay. Let's hit proc. Huh. What? Why it doesn't do anything? Select debug target. Huh. Program. Okay. Okay, connect. Yeah, what happens? Why it doesn't do anything? Did I break this already? Build successful. Program. Ha! Did you get this one working? This is a new problem for me. Oh, okay. KitProc version. Please use PSoC programming GUI to upgrade firmware. So we need to use the PSoC programmer separately. Okay, I think you have the same problem. Do you? Okay, let me try to fix that one. So, Where's the programmer? Okay. I think I need to find it from here. Cypress. Ah! I hate when it happens. Where's the Cypress? Installer. Creator. Designer. Programmer. Okay. All right, so the fix is you need to go here and is there. Where's the Utilities tab? Where's the utility? Ah, there we go. Yep. You need to go to find the PSoC programmer from menu, from Windows menu. Then go to Utilities tab here and click Upgrade Firmware. So the problem was that these were earlier generation the devices, and our programmer is basically our latest model because we just took it today from the Cypress pages. So basically we just need to upgrade the firmware first. Good. And by the way, if you want to this erase block, if you have a device with locked flash, program flash, and you want to use that again, you can erase the whole block and then basically you lose everything, but you know, you can still read work with the device. Okay, but anyways, my programmer now works just fine, I hope. Now I can go here and do the programming. Yes, now it started. Finish programming. Whew. It's not blinking that fast anymore. Okay. Some more small glitches on the way, but anyway, so now it works just perfectly. Getting there? Ah, yes, done. Now you can program it. Yeah, use the other one, that one. Ah, okay, now you need to go stop the debugging mode. Okay. Does it work? Yes! It's so exciting. Okay, yeah. So that's how you make programs for the systems. So we started from top design, meaning the hardware part, added some blocks. This time my block was just the LED one. Then allocated the pin, then did something for the code. Okay. Now I trust that if you get this one done, you can then go and let's see, not there. On exercise 1, there's a pin input. Pin input. Modify the previous design. So you need to add their input pin, digital input pin, connect it to port 2 pin 2, which is actually connected the user button, which is next to LED. There's a small micro switch, push button. It's connected here. They modify the code so that it blinks only when the button is pushed. That's very simple. Basically, what you need to do is just read the value of that pin using the API. So you need to check the data data sheet again. Coffee break. Okay. Yeah, read the data sheet, check how you can read value from the pin using the API, and then just modify the code. Very simple thing. All right. That you can work on by yourself, but actually that one will end the recording of the video. I will be